At this point in the course, we have our research question and our hypothesis about the variables that might answer that question. We've figured out how to measure those variables and identified a method of collecting data, collected the data, organized the data, and we've begun assessing our variables. Now it's time to start evaluating the relationship of one variable to another. Many of our research questions concern the subjects of correlation and causation. We've discussed these subjects previously, but in this lecture, we're going to examine them more closely in the context of data analysis. Correlation is another word for relationship or association. It refers to the idea that two or more variables are related to each other, that as one changes in value, the other does too. An example of a correlation would be that as carbon dioxide levels in the atmosphere rise, so too do average global temperatures. As one goes up, the other does too. Causation, on the other hand, is the idea that the change in value in one variable causes the change in another variable. This is a stronger statement than correlation. With correlation, it might just be a coincidence that two variables seem to change values concurrently, or we might not be able to pinpoint which variable is causing the change in the other. With causation, we're claiming that changing one variable causes the other to change as well. A lot of debates arise over whether an observed correlation implies causation. I just mentioned that carbon dioxide levels and global average temperatures are correlated. Most climate scientists claim this as a causal relationship and offer theories and evidence to support that claim. Climate skeptics usually acknowledge the correlation, but some claim it could be a coincidence, that is, not a causal relationship. Think about how the difference in those two terms influences policy. If we know this to be a causal relationship, then that implies that action taken to reduce carbon dioxide levels in the atmosphere could reduce global warming. But if you doubt a causal relationship, then such actions would be a waste of time. So when looking at the relationship of one variable to another, we have to consider the differences between correlation and causation. How do we know that correlation doesn't always equal causation? In an earlier lecture, we discussed my adventures in spinning, the stationary bike class where you control the resistance that you face. I noted that my feet went numb during the class, and a friend recommended that I should change my knee position on the bike to avoid that. I did, and the numbness went down the following week. The easy thing to do is to conclude that changing my knee position caused the numbness to decrease. But that isn't exactly right, is it? Just because I made one change and saw a different outcome doesn't automatically mean that the change I made caused that outcome. It could have been a number of other things, that in the second class I drank more water, that my shoes weren't laced as tightly, that I focused on wiggling my toes throughout the lesson, or just that my feet started to adjust more to spinning. Just because I take one action and something changes doesn't mean that my action caused that change. In the language of methods, we might say there was a correlation between my change in knee position and the numbness of my feet, but we can't claim that changing my knee position caused a reduced numbness in my feet. Now, you may be thinking that this is due to not having enough data. As we've talked about before, you can't really claim anything with only one data point, not even correlation. So it's not quite right to say that there was even a correlation between my knee position and numbness, not without a lot more data points. Let's say for the sake of argument that we gathered that data. We got a number of new spinners and split them into two groups randomly. We ask one group to use poor knee position and the other to use proper knee position. Then we measure their foot numbness after the session. And let's say that we find that 70% of those using poor knee position report foot numbness, and only 30% of those using proper knee position report such numbness. Aha, you might say, causation. Well, no, not really. Now we can say we might have a correlation. It seems that knee position and numbness go hand in hand, that as one changes, the other does too. But there are plenty of alternative explanations for this. For the moment, let's put aside concerns about the reliability of the data collection. It's possible that people are systematically over or underestimating their level of numbness or their ability to maintain a particular knee position. For now, let's pretend that our data are perfectly reliable. Why might we still say that knee position might not cause foot numbness? Well, the key problem is that we haven't eliminated alternative explanations for our results. There might be some key third variable that affects both knee position and foot numbness that we're overlooking. And this third variable might be the real cause of foot numbness. But if we don't know to look for it, it's easy to just assume that knee position is the culprit. Well, what might some of these third variables be? One possibility might be your speed on the bike. Perhaps the faster you go, the harder it is to maintain good knee position, and the more strain there is on your feet. Maybe not drinking enough water causes general fatigue, making it more difficult to maintain proper knee position while also making your body seize up more. We'd want to include a lot of controls in our experiment so we can isolate the impact of our independent variable, knee position, on our dependent variable, foot numbness. The key idea here is that correlation is necessary but not sufficient to establish causality. We need to find a correlation as one step on the path to show a causal relationship between our two variables. It is necessary, but just finding that correlation is not enough to say that change in one variable causes change in another. By itself, it's not sufficient. We need a few extra steps for that. Before we move on, I just want to warn you. Once you internalize this lesson that correlation doesn't imply causation, be prepared to become very unpopular in casual conversations. Friends will say, "I had a zit and I used this cream on it and it went away, so the cream helped." And you'll find yourself replying, "Well, maybe, but there are a lot of other reasons why it might have gone away." Your friends are looking for affirmation and support, and with you will instead find skepticism and qualification. This is the price of learning research methods, and as a fellow unpopular conversationalist, I apologize. Okay, so how do we know if we're dealing with correlation or causation? Well, there are 4 requirements to establish a causal relationship between two variables. Step 1 is to establish a correlation between the two variables. Again, this means that as we see change in the presence or value of one variable, we also see a change in the presence or value of a second variable. But just because you establish correlation doesn't mean you have causation. I know I keep repeating this. Do you believe me yet? Let's tackle this another way to make sure we're all really clear and ready to become unpopular with our friends. Let's say we establish a correlation between two variables, say their education and income. That makes sense, right? If we asked 500 people what their annual income is and the highest educational degree they've achieved, it probably wouldn't surprise anyone if those with higher levels of education had higher levels of income and vice versa. But if you immediately assume that getting more education means you're going to earn a higher salary, think again. There are a number of possible ways to interpret that correlation that don't indicate a causal relationship between education and income. The first possibility is the one that probably came to your mind first, that higher levels of education cause you to have higher levels of income. That makes sense. It gives you access to higher paying jobs that typically require a college or advanced degree. But there's a second possibility. Can't income levels influence your education level? Anyone who's ever faced a decision about taking on student debt knows the role that their current income plays in whether or not to go for a degree. So the causal direction might actually be reversed, with income affecting education rather than vice versa. The truth might be a mix of the two, actually, where there's a feedback effect between income and education, and they actually affect each other. That's our third possibility. Possibility number 4 is that some other factor causes both high levels of education and high levels of income. Perhaps coming from a wealthy and well-connected family is what matters. A wealthy family can both pay for your education and use its networks to secure you a high-paying job. We call this a spurious cause, and we'll return to it a little later. A fifth possibility is that this supposed relationship is a complete coincidence. Sometimes things happen at the same time without actually being related. For example, if I told you that in my study of people's breakfast preferences that those with black hair prefer eggs in the morning while those with blonde hair prefer waffles, you'd probably call that a coincidence, even though technically we found a correlation between hair color and breakfast preference. There are a number of other possible explanations actually, but reviewing these 5 shows you that it's a logical fallacy to assume that just because we find a correlation that we've established causation. The key is to recognize that just because 2 things happen at the same time or in sequence doesn't mean one causes the other. Step 1, finding correlation between our variables, is not enough by itself. Step 2 helps us there. One way to know if our correlation is a simple coincidence or not is to have a strong explanation for why and how these 2 variables might be related. Does it make sense that one variable causes the other? Step 2 is to establish a theoretical relationship between the 2 variables. Earlier, I said that income and education might be related. Did you notice how I immediately offered a theory of how that might be the case? It's plausible to argue that achieving a higher level of education would give you access to higher level jobs, thus leading to higher incomes than those with lower levels of education. Compare that to my example about hair color and breakfast preferences. There's no real rational explanation for why either hair color or breakfast preference would impact each other. I don't have a theoretical explanation, so making the case for causality is pretty hard. Okay, let's say we found a correlation and we have a strong theoretical explanation for why one might cause the other. Step 3 is to establish temporal order between the 2 variables. This is a formal way of saying that if you're going to claim that some variable x causes change in some variable y, you kind of have to be able to show that x occurred prior in time to y. This is simple in theory, but can be difficult to do in practice. It makes sense that a cause has to occur prior in time to an effect, so to establish causality, you have to show the cause occurs first. But we don't always have access to that information. If you do a survey on income and education, for example, you might not ask about the timing of when someone got their high-paying job versus their degree. We don't have the information to establish temporal order, so establishing causation beyond any doubt is going to be difficult. This is really important in medical research. We need to make sure that the symptoms of a disease changed after the introduction of new medication, not before, in order to really establish whether those pills made the difference. This is why your doctor may get annoyed with you if you can't give an accurate medical history at your appointment. But again, just because you establish that one variable occurs prior in time to another, it doesn't mean that the first one causes the change in the second one. Let's say you've established a correlation, found a convincing theoretical explanation for a causal relationship, and shown that your explanatory variable x occurred prior in time to your dependent variable y. You still need step 4. Step 4 is to eliminate alternative spurious explanations for the relationship between 2 variables. This means we need to make sure that there is no third variable that's actually driving the correlation between x and y. It's possible that the correlation between x and y is actually caused by some third variable. Let's call it z. When you have a spurious cause, what's really going on is that z is changing, and z's change is causing the change in both x and y, rather than x itself causing the change in y. Let's put that in easier to understand terms. The common example is that of ice cream sales, your x, and violent crime, your y. There is a statistical finding that as ice cream sales rise, so too does violent crime, and vice versa. Now, It's possible that ice cream causes violence. I know if my mint chocolate chip cone falls to the ground, I become completely enraged. And apparently I threw a number of fits as a child over lost cones. But this rationale probably fails step 2, our theoretical explanation test. More importantly, it fails step 4, the spurious test. Is there some third variable z that might explain why ice cream sales and violent crime seem to rise and fall at similar times? Well, when are both ice cream sales and violent crime likely to increase? In the summer, when it's warm out. In the dead of winter, no one wants to either go out for ice cream or to be standing outside looking to rob people at gunpoint. Both are, I understand, much more pleasant in warmer weather. So in this case, Z, or temperature, is driving the change in both X, ice cream sales, and Y, violent crime incidences. X and Y are correlated, but X isn't causing Y. So to establish correlation, we need to eliminate these spurious explanations. One way to do this is to hold all variables other than our independent variable constant. If we know that the only variation in our study is that of the independent variable we think is relevant, then that gives us more evidence that X, rather than Z or Q or some other variable, is driving any perceived change in Y. Statistical software can do this for us, which is why we often turn to what's known as regression analysis to help establish causality, and we'll do that in our next lecture. As you can already see, though, establishing correlation is just one of 4 things we have to do to establish causation. It's much easier to show that correlation exists between 2 variables than that causation does. And this is why we tend to just conflate the 2 in daily conversation, and apple a day keeps the doctor away. At this point in our course, we're ready to actually conduct the data analysis necessary to evaluate whether our chosen variables are related to each other. When evaluating whether or not a set of variables are related, or correlated, there are typically 2 broad outcomes. Outcome number 1, there is no relationship. No matter how we change one variable, there's no apparent effect on the other. This outcome supports the null hypothesis and casts doubt on our hypothesis. Remember, no matter what your hypothesis is, it made some kind of claim about a relationship between variables. If we find no relationship, then our hypothesis isn't supported, and the null hypothesis, which states simply that no relationship between these variables exists, is supported instead. Outcome number 2, there is a relationship. It might be weak, it might be strong, or it might only exist under certain conditions. It might be positive or negative or curvilinear. We cannot reject the null hypothesis. So how do we know which outcome we've got? Once we have data, we have several tools to evaluate whether or not a relationship exists between 2 variables and the strength, direction, and precision of any relationships that do exist. Let's look at 2 such methods: examining scatter plots and calculating the correlation coefficient. First, let's look at scatter plots. A scatter plot is a graphical depiction of data where we plot data points on an XY axis. For each case in our study, we plot its value for X on the X-axis and its value for Y on the Y-axis. We can do this by hand or have software do it for us. Once we have all our data plotted, we get a visual representation of the relationship between the 2 variables. By examining that image, we can figure out a few things, such as whether a relationship exists, as well as the form, direction, and strength of a relationship. Imagine, for example, that you see a graph that looks like a horizontal line in the center. So all of your data points are on a single value of Y, while your X points vary widely, giving you a narrow horizontal line of points. Would this indicate a relationship between X and Y? Before you answer, think about what a relationship would mean. A relationship, a correlation, means that changing the value of X coincides with a change in the value of Y. In this case, our visual image tells us that there is no relationship between x and y. X is changing a lot, but y isn't moving at all. So a change in x does not correspond to a change in y. If your graph looks like this, you can safely say that your data indicates no correlation between the two variables and that the null hypothesis is supported. If you had a narrow vertical line, this would also be true. That tells you that for any given value of x, y is changing dramatically, meaning that it's not x that's causing the change in y, but some other variable. And if you had a completely random set of points with no discernible pattern, you'd again be pretty confident in claiming no relationship exists between x and y. But let's say that you graph your points and instead you see a pattern. Say you could draw a straight line through your points, diagonally up from the bottom left of your graph where the two axes meet to the top right. What could we say there? Well, that would tell us that as the values of x increase, as points move to the right, y is also increasing. The points move up. This would indicate that a relationship exists. We call this a positive or direct relationship. It's positive because an increase in x correlates with an increase in y, and at the same time, a decrease in x correlates to a decrease in y. That's also called a positive relationship because both variables are moving in the same direction together. As one goes up, the other goes up, and as one goes down, the other goes down. Let's say instead that the line starts in the upper left and goes diagonally down to the bottom right. In that case, we would also have a relationship, but it would be a negative or inverse relationship. As x increases, y decreases, and vice versa. We use the terms positive and negative to describe the direction of a relationship. Let's say that our hypothesis is that an increase in education level leads to an increase in income. If we plot the data and see a diagonal line from the bottom left to the top right, this is telling us that there's a positive relationship between education and income, that an increase in our x, education, corresponds to an increase in our y, income. That would seem to support a rejection of the null hypothesis. If instead the line ran from the top left to the bottom right, that would still indicate a relationship exists, but a negative one, the opposite of our hypothesis. We can still probably reject the null hypothesis, but we might have to reevaluate our theory at that point. We've discussed positive and negative relationships before, and that there are limits to the use of that approach in hypothesis writing. We need to have data at least at the ordinal level of measurement for it to make sense. Remember, at the ordinal level, we have some sense of being able to place our measures in ranking order, such as first, second, and third place. If you can't at least rank your variable values or put numbers on them, then the idea of positive and negative relationships doesn't make any sense. Remember, a positive relationship means that as x increases, we expect y to also increase. Without being able to order your variable values, that doesn't make sense. Imagine trying to say that there's a positive relationship between religious denomination and hair color. What does that even mean? As your hair goes from blonde to black, your denomination increases? Both variables are nominal variables. They're measured purely by different unranked categories. For hair color, that's a descriptive measure such as black, blonde, red, multicolored, etc. For religious denomination, it might be Protestant, Catholic, atheist, Muslim, Jewish, etc. Neither variable can be said to increase or decrease, so we would never say that there's a positive or negative relationship there. A traditional scatter plot would not be particularly useful for that data. So far, we've talked about whether we see a relationship in our scatter plot and the direction of that relationship, but we can also say something about the form and precision of our plot. The positive and negative relationships we discussed earlier are both linear relationships. They're straight lines from one point to another. There are other forms we might see, though, such as curvilinear relationships. In those cases, x and y might have one direction in some ranges of their values and then change to another in later values. This could result in a C shape, a U shape, or a sort of curved lowercase r shape. You might see a sharp slope to start with an almost straight line, as a small increase in x leads to a massive increase in y, while higher values of x lead to only smaller changes in y, or no change at all. The classic example of this is the relationship between age and height, which we've discussed previously. Babies and children grow quickly, leading to that sharp increase, but by the end of their teenage years, we reach a plateau as a higher age doesn't increase height. And at the far ranges of x, we might even see a dip, as sometimes in our elderly years, we actually get shorter. So that's form. The final piece of information we get from a scatter plot is about the precision or strength of the relationship. If the dots from our graphed data are very close together, that indicates that the relationship is pretty strong. If they're further apart and it's harder to see a pattern, then the relationship is weaker. That's not very satisfying, is it? It's a pretty imprecise measure of precision. At this point, it's better to turn to our statistical calculation of the correlation coefficient, which can give us much better answers about the strength of a linear correlation, while also telling us whether one exists at all and the direction of the relationship. The correlation coefficient is also called Pearson's R. Carl Pearson was one of the fathers of statistics, writing in the late 19th and early 20th centuries. As it happens, he was also a prominent proponent of eugenics, the pseudoscientific effort to breed improvements in the human race, but that's a little beside the point for now. The coefficient is a way of testing to see whether a linear relationship exists, and if so, how strong it is. As with most calculations in this course, I'm not going to go into the math on Pearson's R. Instead, let's focus on what it tells us and why it's useful. Pearson's R is going to analyze our data on two variables and calculate a number between 1 and -1. A positive one would indicate a perfect, positive, linear correlation between our two variables. A negative one would indicate the reverse, a perfect, negative, linear correlation between the variables. What do you think a 0 would represent then? It would mean no relationship at all. So this one statistic itself tells us a lot about whether a relationship exists and what direction it takes. What about strength? R can help us there too. If we look at the absolute value of R, ignoring the positive or negative signs, we can tell a lot about the strength of the correlation. As we just learned, a 1 or -1 would be a very strong relationship, a perfect correlation. And a 0 would be a non-existing relationship. But what about the numbers in between? Well, anything between 0 and about 0.4 on either side would typically be considered a pretty weak correlation, nothing to get excited about. Between a 0.4 and a 0.8 would be a weaker to a stronger relationship, while anything between 0.8 and 1 would be very strong. Now, if you really want to say something about the strength of the relationship, square the value of R. This is called, fittingly, R squared, and it tells you how much of the variation in y is explained by your x. It's reported as a percentage. So if you have a Pearson's R of 0.8, squaring it gives you 0.64, meaning that 64% of the variation in y can be explained by our x. That's really good. All statistical programs will be able to calculate R and R squared for you. In a typical spreadsheet program, simply select the two variables of interest and use the formula for the correlation coefficient. That will give you the value of R. And if you square that number, that is multiply it by itself, you'll get R squared. We have one more thing to do with our coefficients. So far, we've only determined whether a correlation exists in our sample of data. Remember that we usually want to say something about a population, though, not just a sample. So we need to see if our correlation coefficient withstands a test of significance. This will tell us whether we can be confident that our results are due not to chance, but to a real finding that can be applied to our population, not just our sample. We can consult a critical values table to tell us whether or not your value for R is significant and therefore applicable to the population. This will tell us the critical value of R needed to determine statistical significance at the 0.05 or better level. Or you can, of course, let a stats program do this for you and tell you whether or not your correlation is statistically significant. Typically, the more cases you have, the lower your correlation coefficient has to be to ensure statistical significance. With a large data set, even a small coefficient can mean significant results. With a small n, however, you're going to need a much larger coefficient to have a significant finding. Basing your findings on a handful of cases means that the correlation needs to be pretty much perfect to have any sense of confidence in your findings. But a large data set requires a much lower threshold. The key here is that finding the coefficient isn't enough. You need to see if it reaches that 0.05 benchmark for statistical significance if you want to tout your results. With both our scatter plots and our coefficients, we've learned how to identify whether a correlation exists between our variables and the form, direction, and strength of those relationships. But as we learned today, establishing a correlation doesn't tell us anything about causation. We need other techniques for that, and we'll start looking at some in our next lesson. In our next lecture, we're going to start looking at bivariate and multivariate regression, a tool that lets us move closer to establishing causal relationships.